Hi everyone, this is the last lecture video for Physics 217. Before I get into the last topic on radioactive half-life, let me just make a couple of announcements for the end of the term here. First of all, I apologize for the delay getting this up. I had some technical issues, but the next exam, the third exam, the final one, it's not a final exam, but it will cover the material from the previous exam, will happen on Friday, December 4th. I will post that exam at noon on December 4th. It will be up until at least noon on Saturday, December 5th. So make sure you prepare for that. I will post some practice problems on nuclear physics and maybe hopefully a practice test, although you may find some problems that are not on this test since things were cut up a little bit differently this term. But look for those in the extra work or extra problems module on Canvas. Also, the last quiz associated with this L22 video should be posted soon as well. It will be due on Friday as well. The last thing that you need to get into me by December 11th is the final report. So those are kind of the last things to finish up the term. If you do have questions, send me an email, or send me an email that you want to meet via Zoom. I can meet via Zoom, but I'm not going to schedule any regular Zoom times. Usually I just find that no one shows up at those times. So if you're interested in meeting via Zoom, let me know and we can schedule a time. Okay, with that having been said, let's go on to half-life. And we've talked about in the previous video several different types of decay: alpha, beta, and gamma decay. Now, for each of those, and when they occur in different elements or different nuclei, they may occur at different rates. But radioactive decay is sort of a probability or a statistical thing in the sense that if you took one atom, you could not predict when it would decay. It could decay very soon, or it could take a long time. So it's statistical in the sense that I usually talk about it with regard to a large sample of atoms. Right? So let's say you start with 1,000 atoms. Generally speaking, after a time equal to what's called the half-life for that particular element, you will have about 500 atoms remaining. Right? So as an example, let's see, let's take carbon-14. So for carbon-14, remember it has 6 neutrons and 8 protons, and it will decay into nitrogen through beta minus or electron decay. And sometimes you'll see this electron called beta minus, and then there's an anti-neutrino as well. But it turns out the half-life for this is about 5,730 years. I'm going to call it T1/2. And so what I mean by that is, let's say you start with an initial number of 1,000 carbon-14 atoms. After a time of 1 half-life, you're down to 500 atoms, approximately, right? So it might be 501 or 502 or 497, but it's about 500. The larger the sample, the closer it is to actually 1/2 of the atoms. But this is after 5,730 years. So now let's say you go another 5,730 years and you get to a time of 2 half-lives. Well, then you have to cut this again in half and you're down to about 250 atoms, right? After, let's see, 11,460 years, you're down to 250 atoms. Okay, and then again, you can keep going more and more half-lives, but what you're always doing is cutting the sample in half once again. All right, so this would be, let's see, 17,000, about 17,000 years. Right, but after each half-life, you cut the sample size in 1/2. So another way to think about it is, let's say I start with 1 as my sample size. Well, it's cut in 1/2 down to 1/2 after the first half-life, to 1/4 after the second half-life, do 1/8 after the third, 1/16 after the fourth. You just keep cutting it in half. So this is the idea of half-life. Now, carbon-14 has half-life of 5,730 years. There are elements that have half-lives of minutes or hours or days. There are also other elements that have half-lives of millions of years. So what it definitely tremendously depends on the particular element that you have a sample of. One thing I want to point out about this is that this is really an exponential type of decay. Right? If you were to make a graph of the number of atoms left as they depend on time, you'd get something like this graph, which I'm just going to take from the book here. This is in chapter 12, section 12.4 of the book. You'll get a graph like this, right? So you start out with n0, number of atoms at time equal to 0. After one half-life, you're down to half the atoms left. 2 half-lives, 1/4. 3 half-lives, 1/8. But you can see the curve kind of looks like this. And it can be described mathematically by an exponential function, is what we call it. You can read more about that in the book. I'm not going to ask questions about that on the test. The main thing is that you realize it's an exponential type of curve, and the concept of half-life is kind of the most important thing for questions on the test. So one other thing I want to point out about the half-life is, let's say you took 2 elements, 2 nuclei, or 2 samples with different elements, and you set them there, right? And what you might do is take your one sample and put a detector out here. It might be what we call a Geiger counter, which detects anytime maybe that electron from beta decay or a photon or something like that goes into the detector and kind of clicks or counts the number of electrons coming from this carbon-14 sample. Now let's say I had 2 samples, right? And they're the same distance from the detector, but they have different half-lives. Let's say the half-life for this one is only 1 hour, and the half-life for the second sample is 1 day. Now you're at the same distance here, we'll call it R. Which detector, which Geiger counter is going to get a higher count? Right, well, it's going to be the one with the shorter half-life. The reason for that is it's decaying faster, right? So if you start with 1,000 atoms, it's going to get to 500 faster. It's going to shoot out 500 atoms very quickly, much more quickly than the other half-life. Now, if you wait, let's say several days, you're basically down to 0 for this, but you might still be getting a click or 2 here from the longer half-life. Right? So it's really a time-dependent thing. Now, another thing that you could do with this detector that I want to point out is, what if you move it farther away? Well, you're going to get less counts, right? Because what happens is this sample is going to shoot electrons or beta particles off in all directions. They're going to go out kind of spherically symmetrically. So you might guess what the dependence would be, right? Let's say when the detector started, it was getting 100 counts per second. What if you double that distance, right? So now you move the detector out to twice the distance to R. How many counts per second would you expect to get? So this is going to be an inverse square law again, because everything is spherical. Those electrons or beta particles are spread over the surface area of a sphere, which is 4 pi radius squared, right? And so the point is, it's going to be 1/4 of the count that you had over here. It's going to be 1/4 of that 100 counts per second, or 25 counts per second. So as you get further and further away from a radioactive sample, you're a little bit safer because of this inverse square dependence, right, of the kind of the activity of the sample that you get when you increase the distance. Very much like Coulomb's law, very much like intensity of a sound wave coming from a point source, right? So this inverse square law appears in many different places. So last thing I want to talk about here are just a couple of quick applications of half-life and radioactive decay. First is, let's start with our carbon-14. Right, again, it decays through beta decay to nitrogen plus our beta minus particle, our electron. And what can happen here is that with carbon-14, living organisms interact with the atmosphere, the air. And there is always carbon-14 in the air. So for example, when you breathe, you're breathing in not just carbon-12, which is stable, but carbon-14, which decays, right? It starts to decay in your body. But it's going to stay in your body because the air you breathe gets integrated into your organs, into your bones, all parts of your body. You're a carbon-based life form. So what happens is once an organism expires or dies, right, well, it stops getting more carbon-14 into its body. It's not replenished. So the carbon-14 has a half-life of 5,730 years. So what you would expect is, let's say you found an old bone or other organic matter that died a long time ago. What you could do is radiocarbon date it. And what you'll then do is look at how much carbon-14 is in the sample, right? If you find that there's 1/4 of the original amount of carbon-14, you can pretty much say that that sample must have died about 2 half-lives ago, or 11,460 years, right? 2T1/2. So it must have passed away 2 carbon-14 half-lives ago, around 11,500 years ago or so. Right, so that's kind of the basic principle of radiocarbon dating. Now you might ask the question, how does carbon-14 stay in the air? Right, well, this goes to a topic I won't spend much time on, but it turns out there's something called cosmic rays, which are mostly protons coming in and hitting the upper atmosphere, hitting our atmosphere. Now, as it turns out, there's a lot of carbon-14 in the atmosphere. And when that proton, for example, hits carbon-14, it can break it apart and actually knock out a proton, is one of the things it can do, and create carbon-14 in the atmosphere, right? So due to these cosmic rays, carbon-14 is constantly being created in the atmosphere. And it fluctuates a little over time, the level, but it remains roughly pretty constant. So we kind of know, roughly speaking, how much carbon-14 there was 11,500 years ago. And from that knowledge, we can radiocarbon date things. Okay, last application here, which is related to medical imaging. How does a PET scan work? So first of all, PET scan is positron emission tomography. And we've talked about the positron in the past. It's the antiparticle of the electron. And this is a second time type of beta decay that can occur. It turns out that instead of a neutron turning into an electron and a proton, you can, when it's inside the nucleus, have a proton turn into a neutron plus a positron, right? And I'm going to call it a beta plus. So the beta plus is just a positron, right? It's E plus. And you get a neutrino, not an antineutrino, as it turns out. But this positron is ejected, right? It shoots out from the proton that's in whatever nucleus that's undergoing this type of beta plus decay, positive beta decay. As it turns out, if this beta plus particle or positron, let's call it a positron E plus, smacks into an electron in your body, for example, so you have E plus plus E minus, they annihilate. Positron electron annihilation. No, what I mean is you don't lose energy there. The energy actually turns into 2 gamma rays. Sometimes they'll write it as 2 gamma. It actually can turn into 3, but most of the time it will turn into 2. But what happens is, due to other conservation of laws, conservation of momentum, these gamma rays have to shoot out in opposite directions. So what is done in PET scan, you basically inject a person with an element that undergoes beta plus decay. That positron, when it decays, will hit an electron in the human body, right? All of your atoms have electrons. It will create these 2 gamma ray photons which shoot out, and around the person are detectors that can detect those photons. Now, by actually kind of triangulating or extrapolating back, you can determine where those 2 gamma ray photons originated from and determine an image of where that is happening, where the gamma rays are being created, where this annihilation is taking place. And that's the tomography part, right? A CAT scan works in a similar way by doing a bunch of X-rays and creating an image out of all the data that is obtained. But in this case, the fundamental thing that's going on is this beta plus decay and then positron electron annihilation. So one way that this works is that you can take, for example, a sugar molecule and attach a tracer element to it that undergoes beta plus decay, may inject it into a person, for example, and that, into their bloodstream. This sugar molecule will go throughout the body, but one thing about cancer, it likes to eat sugar. And so it will tend to concentrate where maybe a tumor is. And you'll see a lot of gamma rays emitted where that tumor is, because the tumor is eating up the sugar, right? It concentrates in that area. So that's a really simple description of PET scan. Again, one relation to the half-life of this is you don't want to use an element that undergoes a long half-life. You want to use an element that undergoes beta plus decay with maybe an hour or less half-life, so you don't have this radioactive element in the human body for a long time. Okay, I think that's good enough for this term. I hope you enjoyed the class, even though it was a very strange term. And we didn't actually get into some things that I usually get into, but hopefully it will help you in your future study of medical imaging. If you do end up ever having questions in the future, even years from now possibly, about physics and how it relates to medical imaging, feel free to get a hold of me. Until that day, I will see you later.